Welcome to Astronomy Daily, your source for all the latest news from the cosmos. I'm your host, Anna, and today we're exploring an eclectic mix of astronomical discoveries and breakthroughs that are expanding our understanding of the universe around us. From scientists who have managed to listen to the music of stars, to the James Webb Space Telescope capturing Jupiter's auroras glowing hundreds of times brighter than anything we see on Earth, we've got fascinating stories to share. We'll also dive into mysterious, unexplained light pulses detected in a Seti survey, examine this week's busy launch schedule across 3 continents, and explore a revolutionary new theory that might finally bridge Einstein's gravity with quantum physics, potentially solving one of science's greatest puzzles. So sit back and join me as we journey through the latest developments from the depths of space to the cutting edge of theoretical physics. Get comfortable, and we'll get started. Astronomers have achieved something truly remarkable. They've managed to peer inside a nearby star by listening to its resonance. Using the same principle that helps geologists understand Earth's interior layers, scientists are now applying this technique to stars. A groundbreaking study published in the Astrophysical Journal reveals how researchers at the Keck Observatory in Hawaii trained their instruments on HD 219,134, a cool orange star just 21 light-years from our solar system, practically our stellar neighbor. The vibrations of a star are like its unique song, explains lead author Yagwang Lee from the University of Hawaii at Manoa. By listening to those oscillations, we can precisely determine how massive a star is, how large it is, and how old it is. While stellar songs have been detected before using astroseismology, they've typically only been recorded for very hot stars. Scientists previously thought the oscillations of smaller, cooler stars would be too subtle to detect, until now. The Keck Planet Finder, an instrument usually employed to discover exoplanets, proved sensitive enough to measure the slight motions of HD 219,134's surface. Over 4 consecutive nights, researchers collected more than 2,000 precise velocity measurements from the star. What they discovered was astonishing. HD 219,134 is approximately 10.2 billion years old, more than twice the age of our sun. This makes it one of the oldest stars ever aged using astroseismology. This breakthrough is particularly significant because traditional techniques for determining stellar ages don't work well as stars get older. One common method relies on measuring stellar spin, as younger stars rotate faster. However, this slowdown becomes less pronounced over time, making it increasingly difficult to date elderly stars. The team also found that HD 219,134 is about 4% smaller than previous measurements suggested. This discrepancy might indicate that cooler stars don't fit the same models used to estimate the size of hotter stars. This stellar music technique opens a new window into understanding the life cycles of stars and will help astronomers better characterize the at least 5 planets, including 2 rocky worlds larger than Earth, that orbit HD 219,134. As researcher Lee puts it, this is like finding a long-lost tuning fork for stellar clocks. It gives us a reference point to calibrate how stars spin down over billions of years. Let's take a look at this week's launch schedule, with a very special event for our listeners down under on the schedule. Space launch activity is ramping up dramatically this week, with rockets lifting off from 5 countries across 3 continents, in what's shaping up to be an extraordinarily busy period for space exploration. Australia is preparing to make history with Gilmour Space, readying its ERIS orbital rocket for the country's first sovereign orbital launch from Bowen, Queensland. The 25-meter-tall ERIS vehicle uses hybrid propulsion technology and could make Australia just the latest member of the exclusive club of nations with indigenous orbital launch capabilities. It is hoped this inaugural launch will take place on Thursday, May 15th, morning local time. Meanwhile, SpaceX continues its relentless cadence of Starlink deployments. The company has already conducted multiple Falcon 9 launches this month, with more planned from both Vandenberg in California and its Florida launch sites. One recent mission marked the 28th flight for a single booster, a remarkable achievement showcasing the company's reusability prowess as it pushes toward breaking its own record of 132 launches set just last year. In Asia, India's Space Research Organization is preparing its PSLV-XL rocket to launch the EOS-9 Earth observation satellite from the Satish Dhawan Space Center. This C-band synthetic aperture radar satellite, also known as RESAT-1B, will join India's growing constellation of Earth monitoring spacecraft. Not to be outdone, China has scheduled multiple missions from the Jiuquan Satellite Launch Center, including a launch of their innovative Zhuke-2E rocket. This vehicle is particularly noteworthy as it's powered by liquid methane and liquid oxygen, making it among the first methane-fueled launch vehicles to successfully reach orbit. Across the Tasman Sea from Australia, Rocket Lab is readying an Electron rocket at their private spaceport on New Zealand's Mahia Peninsula. Their mission, whimsically named the Sea God Seas, will deploy a synthetic aperture radar satellite for Japanese Earth imagery provider IQPS. This global surge in launch activity reflects the increasingly democratized access to space, with both established space powers and emerging players contributing to a diverse ecosystem of launch vehicles and capabilities. From SpaceX's workhorse Falcon 9s to Australia's debut ERIS vehicle, the variety of rockets taking flight demonstrates how space access continues to evolve beyond the exclusive domain of just a few nations. Next up today, let's return to a favorite subject here on Astronomy Daily. In the vast expanse of our universe, the search for extraterrestrial intelligence continues to yield fascinating results, though not always the kind we expect. A recent multi-year survey has detected something truly puzzling that has astronomers scratching their heads. NASA veteran Richard Stanton has been conducting an optical Seti survey using a 30-inch telescope at the Shea Meadow Observatory in Big Bear, California. Unlike traditional Seti efforts that focus on radio signals, Stanton's approach looks for unusual pulses of light that might indicate technological activity around distant stars. After observing more than 1,300 sun-like stars over several years, Stanton detected something extraordinary. Two fast, identical pulses of light from HD 89389, an F-type star located about 100 light-years from Earth. What makes these pulses so intriguing is their peculiar pattern and timing. They were separated by exactly 4.4 seconds and showed nearly identical fine structure patterns within each pulse. The star's light briefly brightened, dimmed, brightened again, and then returned to normal, all within about 0.2 of a second. This pattern is far too strong and structured to be explained by random noise or atmospheric turbulence. As Stanton noted, how do you make a star over 1 million kilometers across partially disappear in 1/10 of a second? Even more compelling, when Stanton reviewed historical data, he discovered that similar paired pulses had been detected around HD 217,014, better known as 51 Pegasi, back in 2021. This G-type star, located about 50 light-years away, is notably the first sun-like star found to have an exoplanet orbiting it. Stanton has meticulously ruled out all the usual suspects. These signals don't match known patterns from satellites, airplanes, meteors, birds, or other common sources of false positives. No movement was detected near the stars during simultaneous photography, and background sensors designed to catch satellites moving close to target stars detected nothing unusual. Various natural explanations have been considered, from atmospheric diffraction caused by shock waves to partial eclipses by distant asteroids. Even more exotic possibilities like gravity waves have been examined. None provide a satisfactory explanation for the precise, repeating nature of these pulses. This leaves open a tantalizing, if remote, possibility that these signals might have an intelligent origin. If so, Stanton suggests whatever modulated these stars' light would need to be relatively close to Earth, implying potential ETI activity within our own solar system. But Stanton remains appropriately cautious. None of these explanations are really satisfying at this point. We don't know what kind of object could produce these pulses or how far away it is. Until we learn more, we can't even say whether or not extraterrestrials are involved. To further investigate this mystery, Stanton recommends using arrays of synchronized optical telescopes to gather more data. If an object is moving between us and these stars, this approach could reveal its speed, size, and distance. Observations from telescopes separated by hundreds of kilometers might also help determine if the light variations originate from the stars themselves or from something closer to home. For now, these unexplained pulses join the growing list of astronomical curiosities that remind us how much we still have to learn about our cosmic neighborhood. The James Webb Space Telescope has given us a Christmas gift that has astronomers absolutely mesmerized. Unprecedented views of Jupiter's auroras that make Earth's northern lights look like a dim flashlight by comparison. On Christmas Day 2023, Webb captured glowing auroras adorning Jupiter's north pole that are hundreds of times brighter than anything we see on our home planet. What stunned scientists wasn't just the intensity, but the dynamic nature of these celestial light shows. Jonathan Nichols from the University of Leicester, who led the study, was completely taken aback by what they observed. We wanted to see how quickly the auroras change, expecting them to fade in and out ponderously over 15 minutes or so. Instead, we observed the whole auroral region fizzing and popping with light, sometimes varying by the second. Jupiter's auroras form through processes both familiar and unique. Like Earth, charged particles from the sun's solar wind get funneled toward the poles by the planet's magnetic field. But Jupiter has an additional aurora factory. Particles ejected from volcanoes on its hellish moon Io undergo the same process, adding to the spectacular display. To capture these details, scientists used a double-barreled approach, combining Webb's near-infrared camera with Hubble's ultraviolet sensors. This dual observation revealed something especially puzzling. As Nichols explained, bizarrely, the brightest light observed by Webb had no real counterpart in Hubble's pictures. This has left us scratching our heads. This discrepancy points to something previously thought impossible, a combination of high quantities of very low-energy particles somehow reaching Jupiter's atmosphere in ways current models can't explain. The phenomenon is forcing scientists to reconsider our understanding of how particles interact with planetary atmospheres. The research team plans to continue studying Jupiter's auroras with both telescopes to better understand the mysterious particle combination reaching Jupiter's atmosphere. Their findings could reveal entirely new details about Jupiter's magnetosphere, the vast region of space around the planet influenced by its magnetic field. For now, Jupiter's dazzling light show represents yet another cosmic mystery waiting to be unraveled, showing that even within our own solar system, nature still has plenty of spectacular surprises that challenge our scientific understanding. Some exciting science news is next. I'll see if I can explain it so it makes some sort of sense. For decades, physicists have been searching for the holy grail of modern science, a unified theory that can bring together Einstein's theory of gravity with quantum mechanics. These two pillars of physics have stubbornly refused to reconcile, creating what many consider the most significant unsolved problem in theoretical physics. Now, researchers from Finland's Aalto University may have made a crucial breakthrough. Mikko Partanen and Jukka Tolkki have developed what they call unified gravity, a groundbreaking approach that could finally bridge this theoretical divide. Their work, recently published in Reports on Progress in Physics, takes a novel approach to a century-old problem. The fundamental challenge has always been one of mathematical language. The standard model of particle physics, which describes the electromagnetic, weak, and strong forces, uses a framework called quantum field theory. Gravity, on the other hand, is described by Einstein's general relativity, which views gravity as the curvature of space-time itself. This clash between the internal symmetries of quantum fields and the external symmetries of spacetime has made gravity extremely difficult to fit into the quantum framework, as Partanen explains. Their innovative solution introduces an 8-component spinorial representation of quantum fields and a spacetime dimension field that allows them to extract familiar 4-dimensional spacetime quantities from an 8-dimensional spinor space. This mathematical sleight of hand enables them to treat gravity using compact, finite-dimensional unitary symmetries, the same kind used in the standard model. What makes this approach particularly promising is that it allows gravity to be represented in flat spacetime using the Minkowski metric, without requiring the curved spacetime of general relativity. This makes it possible to write gravity in the same mathematical form as the other fundamental forces, Partanen notes. That's something we haven't been able to do before. The researchers have gone beyond just theoretical formulations. They've derived Feynman rules for unified gravity, essentially the mathematical instructions used to calculate how particles interact in quantum field theory. Their analysis suggests that all infinities in the equations could be absorbed into a small number of redefined parameters, suggesting the theory could be renormalizable. a critical feature that previous quantum gravity theories have struggled to achieve. If proven correct, unified gravity would have profound implications. It could provide tools to explore the universe's most extreme environments where both quantum effects and gravity matter, the interiors of black holes, and the moment of the Big Bang itself. Without a quantum theory of gravity, we can't fully describe what happens at high energies where space and time behave very differently, says Partanen. Their theory might eventually answer fundamental questions about why there's more matter than antimatter in the universe, or how space-time behaved in the earliest moments of existence. While the theory still needs to be proven at higher orders of quantum correction, the researchers are optimistic that unified gravity could do for 21st century physics what Einstein's general relativity did a century ago, open entirely new frontiers of understanding and technological possibility. Phew, how'd I go? Hopefully that all made sense. On that note then, we'll wrap up today's journey through the cosmos. From listening to the music of stars and tracking this week's busy launch schedule, to unexplained pulses of light that have SETI researchers puzzled, Jupiter's spectacular auroras, and a potential breakthrough in unifying physics' greatest theories, we've covered quite a bit of ground among the stars. I'm Anna. Thanks for joining me on Astronomy Daily. If you'd like to stay updated on these stories and more, visit our website at astronomydaily.io, where you can sign up for our free daily newsletter and catch up on all the latest space and astronomy news with our constantly updating newsfeed. And don't forget to follow us on social media. Just search for Astro Daily Pod on Facebook, X, YouTube Music, Instagram, Tumblr, and TikTok. We'd love to continue the conversation about today's fascinating topics with you there. Until next time, keep looking up.